And I really want to make this clear because what you just said is a little bit... X is some input for this function, period. But it is the variable for this function, right? Because I can go further or not as far, so that's the variable for this dude. So for some given X amount out, if I go just a little bit further and investigate how much bigger the area gets, that will be related to what the derivative is.
Correct.
Beautiful. So, look what I get here. If I divide by H. Oh my God. And of course, what are we doing on this side? I'm letting H go to down there, infinity.
It's
So, what does this represent? G prime.
our G prime.
And of course that equals f of x. So, real quick, here's the key. And I really like that reaction. That's kind of cool. Here's the real big thing, though. This is what we need to understand. What we just shown, if g prime of x, if the derivative of g is little f, then related to this dude, what is g? Yeah, it's big ass f, right? Now don't worry about the plus c's right here at the moment. Somewhere there's a plus c in there, but screw it. What's more important is the idea that that this g function, and in fact, what is the g function?
That is the area under the function.
It was in 4.
Or wait, no, because yeah.
The G function? It's a 4.
Oh, it's right here. It's the integral, right? So what this is saying is, if I took, now here's the fundamental, and very soon we're going to get part 2, which is the fundamental theorem of calculus part 1 is interesting, but it's not used nearly as much. Fundamental theorem of calculus part 2 is the one that's going to run your life and mathematics basically from here on out. So it sounds a little more important. So let's do the fundamental theorem of calculus part 1. Part 1. And what this says is basically what we just figured out. If g of x is the integral from a to x, f of t dt, then g prime of x equals f of x. So specifically, and this actually sets up exactly what we want. If the derivative of an integral is the function, then the integral of a function is its antiderivative. I mean, that sets up exactly what I desperately wanted. Was a connection between finding the area, which is what this represents, and finding an antiderivative, which is what this is all about.
So the integral of x to a f t dt is big F x, correct? Or no?
You lost me there. Say again?
So that integral right there, is it equivalent to the antiderivative of x or no?
Yes, it is, and we'll talk more about. And I'm a little loose here. I was trying to go for the idea because I kind of lost my A dude in the process, but that's all right. I'll deal with it. So it's got to come back in. But the more important idea I was trying to get at is the antiderivative is directly related to this. Fundamental theorem of calculus part 2 sets up that direct relationship. So real quick, concrete example, right? Because we've been having non-concrete discussions so far. I think as non-concrete as you can get. So if I said find the derivative of oops. Do that, sure. I want you to realize this is almost like when you first learned sine, and then what's the opposite of sine?
Negative cosine. Or
What's the opposite of sine? Inverse, the inverse sign, the arc sign, right? I love how you guys are online. No, I'm talking pre-calc. So we're learning the opposite function of something right now. So people take this too far. The cosine is not going to show up in the answer here. Because, for example, if I said, what's the cube root of x squared cubed? It's x squared is actually the 6. The cube doesn't get in there. It kills that, and that's left alive, right? So if I'm going to take the derivative of what we now know is effectively the antiderivative of this, of course I'm going to get this. But it's got to be evaluated where?
Between A and B.
No,
Between x.
at x. So this will be g prime of x will be sine of x. And again, what this really, I want you to see. So if I have the sine function, and of course I had to pick 3 of us, too, and that 3, let's see, where am I? Here's pi, so the 3 is about like here. So the, so this g of x, now stay with me. This g of x is the area from 3 up to some x, right?
Sure.
So in this case it would end up being negative, because most of it is below the x-axis. Is that cool? Being a negative area. So if I want to go one step further, really, and I'm going to add this, that is effectively that value. That's how much I'm going to add. If I take an infinitesimal step forward, I'm going to add that amount to it.
Is that just that sign of x right there just only the distance, that little tiny infinitesimal amount right there?
That's that amount there, yeah.
But it's not the whole area plus that amount.
No, exactly. It's not the end result. It's how much g is changing.
Okay.
Is related to sine x, because I keep adding that much on. It's like those little pieces of tape that I'm going to add on. Yeah.
So g prime is just the original function of the integral?
Yeah, it effectively undoes this integral. And this constant doesn't matter because it's all about how much is changing. Yeah.
So when you're talking about adding layers, you're talking about like a rectangle with like near 0 width and like sine x as the height?
Not quite.
Okay.
But the height will be sine x, right?
Yeah.
And that was the whole thing we were doing earlier, was showing that it's the exact same thing as if I go one step out, I'm just going to add the circumference on. So if I go one step out here, I'm just going to add a height in. That height
is going to be the area of sine x, basically.
That's going to be the value of sine x.
Okay. And
Okay.
Then, so then would you, if you wanted to know, that just tells you the change though, right? It doesn't tell you anything else about the function.
It just tells you the change, yeah.
Okay.
The rate of change. Cool. Yes.
So that space right there is sine x between the 3 and the x.
This function is sine
Yeah.
of t. Yeah.
But the space between 3 and x, that's what's confusing me, how we got g prime.
G of x is the area between 3 and x.
Oh.
That's what g of x is.
Okay, I see.
So if I go an infinitesimal step out, how much will it change by? It'll change by sine x.
But it's only going towards the direction away from x. So if you're going in the direction away from 3, like the opposite direction, you should be going sine x to the left.
X itself can be any value. So I've just drawn a representation.
Where did our t's vanish off?
But your question is,
So what if x?
this implies that I'm moving in the positive direction.
Yes.
Yes.
So, but we can't have x equal something less than a, can it?
Sure, of course you can.
So then it,
Because that's the whole idea we're talking about just switching our limits,
Okay.
right? And then making it the negative of what it was. Because I agree with you. I'd rather go from smaller to bigger. It makes more sense. So if you ever have it flipped around, you just flip it back and make it negative. Yep.
Why where did the dt there go when you took the derivative? Oh, is it just because is that like a constant or something? So it goes to 0, or I guess that wouldn't happen.
You're saying dt is so small that it doesn't exist. What are you trying to say?
No. The utility of this is actually kind of lost in what this takes the place of. So remember, this takes the place of the limit and the summation.
Uh-huh.
So together they represent what we're actually doing to sine.
So then when you take the derivative, you basically just shoot them both out of the picture.
Take the integral. Take the
integral.
Integral. Okay. All right, so this is the part that's not used quite as much. But the minute we set up a function, we should think about what its derivative is. Yeah.
I understand that the derivative is the opposite of the integral, so that's why you get sin x, but why are there not two things instead of sin x, considering there's a 3 and an x?
So just a second. Let me see how I can address this directly. So the value of how to explain this? I'm trying to capture because this would end up being a constant, so the derivative would just kill it.
Yeah.
But I'm trying to really figure out how to show that nicely.
Oh, so you're saying is you would put the x and the 3 into the sign and then differentiate it, and so you would cancel the constant, and you just get the answer. Wait, never mind.
What would be sin
Let me do the
3?
part 2, and it's going to come out in that.
Okay.
Okay. It's going to come out in part 2. Part 2 is going to be nice. We can get to a point. Well, let's get there. And then I can come back and talk directly to what you just were asking. Because that's a good question. That's very crucial to know why the hell that just kind of... It doesn't even matter what I put there. I could put 78 there. I could put 18 billion there. As long as it's a constant, the fundamental theorem of calculus 1 eats it up, spits it out. And it's sort of related to... I mean, it's exactly related to... I just can't figure out how to really represent it nicely there, but it's exactly related to... what's the derivative of this? 2x. Well, what's the relate? Okay, all right, okay, yeah, okay. What's the derivative of this?
2x.
Oh shit! All right. I mean, it's exactly the same idea, just the integral equivalent. Because I am taking a derivative. This would end up being the constant in the problem. It's easier to represent it once I get part 2 down.
Okay.
But that's the general idea of what happens.
So you're saying it has to be a constant in order for the fundamental theorem to work, correct?
There has to be a constant here, yeah.
So if you were to have, instead of having x on top, you had like a y. You had x on bottom. Could you do that, or
It's not easy.
because you're dealing with two different derivatives? Is that why?
Let's go a little further. And then we'll come back and talk about the weirdness. Right now, we are trying to get the basic idea down. And then any rule we know about differentiation can happen in this kind of problem. So I could have from 3 to x squared. That would be a chain rule. Because there's an x squared inside of my integral. Right? So all those rules still apply. But it's harder, of course, when you have variable expressions on both ends. It gets a little freakier.
What is the hypothetical constant?
Oh, and then the whole thing is a constant, so that would be nice. If this was 3 to 7, this kind of goes a little bit towards your question. If this is 3 to 7, how do I take the derivative of it? Well, what is integral of sine t dt from 3 to 7? What does that end up being?
There's just two constant numbers.
It's just a number. It's the area from 3 to 7. It's a definite number. So what's its derivative? Beautiful, 0. So here, the half that is a constant, of course, doesn't show up because it's a freaking constant. The derivative is going to kill it. Well, you'll see it a little bit easier here
So we would
if I ever get there. Yes.
What would happen if 3 was on top and x was on the bottom?
Then you just flip it by putting a negative out front.
Huh.
Yeah, so that's the utility of that. You don't do it at some weird ass time. You do it when something's not in the right place.
Would
You
that
just
be
flip it and put a
minus
negative.
sin x then?
It would be minus sine x.
Okay.
Yep. Good. Okay.
If they were both constants, like what he was asking, you'd be able to find the area because it's just two numbers, correct? You just wouldn't be able to get a
Derivative is
derivative.
0 though.
Say that one more time.
So you wouldn't be able to get a derivative, but you'd be able to find the area. So because you're between two numbers, or because you're between two numbers. Because it's 3 and 7, you said if x was 7.
Yes.
So you'd be able to find the area because it's from 3 to 7, but you wouldn't have a derivative because it'd be 0 with constants.
Yeah, the area would be a constant. It would just be a number. Yeah. Okay. So what I want to do, here's the fundamental theorem of calculus part 2. And let me state what it says, and then we'll try to prove it. What it says is this. I don't need a T in it now.
Can I just triple check those F's on the other side of the equal sign on the right side? Those are capital, right?
Yes, good. Those are big ass F's. Yeah. So that the integral of this is what the result of the theorem is. It says that the integral of f from a to b is equivalent to the difference in the antiderivative evaluated at the endpoints. I like that. I don't know. So the area under the function f from a to b is equivalent to the difference in the values of the antiderivative at the endpoints. Okay. Which kind of makes sense based on what we were talking about earlier. And actually, we sort of saw that with the 4b minus 4a when we integrated 4. But that was too simple of a function to trust. Okay, so if I set up, let's see, yeah. How do I do this? If I set up g of x, and that's going to be, no, I don't want to go that way. Which way I want to go? So this is from a to b, this function, f of x, whatever it's doing. So it's that area underneath there. Right, that's what this represents. And that's just the difference between two antiderivatives. So if I have what we saw earlier, which way do I want to go this? Oh, okay, that'll work. Yeah, okay, good. Let's remember this here. This was how I defined that, right? That's how I defined the g of x earlier that we were using, right? So g of b would be what?
So it goes to b, right?
Big F.
No, yeah. This is getting a little too far away. But just based on this, g of x is a to x f of t dt. So g of b is a to b f of t dt, right? How we doing? In fact, yeah. Here we go. Oh, let's see. Which way I want to go here. Oh, okay, that's it. Okay. So what I want to do, and I think I was being a little too specific with my little a dude down there. He's part of this problem. So I want g of x to not be dependent on a. So what I'm going to say is g of x is equal to this. So g of b is equal to this. So it kind of catches up to what's going on. So we have this function, this f of t. G of x goes from c to some point x. Now I have my points a and my points b. How we doing so far? And that's what I really want to talk about from this theorem. How we doing?
So we're trying to find g of x, or we're trying to find g of b?
No. So what I'm trying to do is prove that this equality is true. Right? So I want to talk about the integral of f of x from a to b. So one way I could try to do this, because exactly what you said earlier, we already know there's a connection between this function and the antiderivative. Right? So that's kind of the go-between. I can use that to go between the two. So this is the definition of g of x. I just have to use the letter c because the letter a is already taken. Are you guys cool with that? It just has to start somewhere. So the letter a is already taken. So I want to use the letter c. So g of b is this, which in g of a is going to be this. So g of a would be this much right here, right? This is g of a. And g of b would be this much.
And then g of x would be g of x, which makes sense.
Okay, all right, so far. Okay. And we know that this is equal to big ass F. Now I gotta be careful. Well, we know that this is equal to big ass F of x. How we do so far? We know that from earlier. We proved that earlier. So from that, we know that this is equal to big ass F of b, right? And we know that this is equal to big ass F of a. So big ass F of b, let's see if this works, because I haven't tried to do this way, equals to integral c to b minus the integral c to a. It's kind of nifty. Now, here's where things get really neat. This is cool. You guys are all suffering. I understand. I forgot the way I wanted to do this, and I've just created a new way. This is going to work. I just realized. So I was a little worried for a second. Stay with me. We proved this earlier. You with me? I'm kind of excited now. This actually works nice. So that means then that this is true all the way through. And this is true all the way through. Right? All right. Now, here's where you kind of need a little side note. Let me see if I can make this make sense. Here's a little side note. Get ready. This is kind of neat because you're going to have to apply what I'm about to say to you. You're going to have to apply it concretely in the next few sections. So if I wanted to integrate from A to B, stay with me now. I could integrate, now this is kind of silly. On one level, this is just like, duh, Jeff. I could say, okay, it's the same, the area from A to B, isn't that the same thing as the area from A to C plus the area from C to B?
Yes.
Kick ass. So this equals the integral from A to C plus the integral from C to B, because I know that these just represent areas, right? So the whole area is the sum of the smaller areas. Amazing, Jeff. Write that in, send it off, get it published. But how the hell does that relate to what I've got written? Can anybody help me out? I do have that there. It's just that my limits are, and I keep saying limits, because that's what we call these actually, the limits of the integration. It's not related to the limit as n goes infinity something. So if I say that, I'm sorry. I'm just so used to saying that. So what's wrong with these? They're backwards. But what rule do I have that will help me?
Just flip them, make them.
Flip them, Jeff.
Flip them rule.
The flip it rule, exactly. Which is equal to the integral from A to B. When you combine those two areas, right? It goes from A to C, and then from C to B.
Are you supposed to flip the B and C?
Say again?
Are you supposed to flip the B and C
No,
also?
because those were positive.
No, I'm leaving him alone. If I flip him, then he's negative.
Okay.
I want to combine those two. Yes. So now this equals the integral from A to B. Because I'm in the way. Like, I know why I can't see. So what the hell just happened? Here's what just happened. To find the integral from A to B of any function, and I want to make this point really big now. T is a dummy variable. I could have used B, W, X, F, D, whatever the hell. So I can put an X back in there. It's not a big deal. It's just the variable that I'm using for the integral. It doesn't matter. So the integral of some function from A to B is equal to the difference in the antiderivatives evaluated at those endpoints.
So the reason we got rid of the C in the integral equation was just because that was a point in between the two, and it was somewhat.
Do it one more time, sorry.
Alright.
Oh, yeah, the C is gone because it's like the middle. So if I say this whole area, do I need C at all? No. So what I did was I took this area plus that area, and now I don't need C anymore because I'm just saying it's from A to B.
Alright.
And then that's it. I love it. So here's, yes, I want to show you a concrete example of what we just did.
So, just get it straight, just those two added are that, right?
Because of this idea.
Because of that idea.
It's since integrals are areas, they have several properties that seem too easy, but they are just areas. So if I can add areas and then eliminate the middle dude, because now I'm going from there to there, that whole area, that's exactly what happens. I don't see a C anymore at the end because I don't need him. I'm just going to go past him and keep going.
So this is based on that diagram, correct?
Sort of. But even if even if things are out of place, areas will be negative. If I'm going from so here it would be
So they don't have to have negative.
C to B and A to C. So if I go C to B, I want to show you this.
So it's like it'd be more.
If I go C to B, that's this whole area.
Yeah.
And then if I go A to C, it's going to subtract that off because I'm going the wrong direction,
Which would be A to
So it
B.
doesn't have to have negative.
and I'll end up with A to B.
Yes.
Okay.
You guys, you with me? So that's a really good example. That's a really good question, but it doesn't matter because the negative idea, if I go backwards, it's negative.
Okay.
That saves my S.
Which is
I thought-
equal.
Sorry. I was gonna say, I thought earlier when you were talking about the negative values, it had to be negative y values, but that makes sense going backwards. Plus,
Yeah, so either it could go below the x-axis or it could be going that way because then the b minus a for that would be negative
Makes sense, yeah.
because now the bigger one is second.
So then, so that right there is equal to g of x, which is equal to.
Let me show you. Let me show you. Here. So that was derivation, which is always awesome. All right. But here is the actual nuts and bolts. What the hell does this mean for me? Point. Right. So we did this function earlier, right?
Yeah.
From this was on the handout from 2 to 5, and what answer did we get?
42.
Yeah, we did this and we got 42. So we're going to redo it using the second fundamental theorem of calculus. And it took us a while to do it, right? And we all loved it, but it took us a while.
I thought you needed a variable on your starting point to do that. I'm sorry. On
What we just proven is that if I want the integral between two definite endpoints, between 2 and 5, for example, I can just use the antiderivatives to find it. Instead of having to go through the whole limit of the sum of the f times delta x.
I see, okay.
You with me? So that's like our chapter 2 is being replaced by our chapter 3. Right? Chapter 2 was limits, and chapter 3 was, screw the limits, let's just do the derivatives. Right? Because now we can start making the rules. So what does this look like now, integration-wise? What would this look like now, integration-wise?
Short and ball, 5 and 12.
Yeah, 2 to 5,
4x dx.
4x dx. Now this is going to equal, let me just write this out, f, big ass f of 5 minus big ass f of 2. Now the reason the plus c cancels is because it's here, and you got c minus c gone. So you don't need the plus c for a what's called a definite integral. This is a definite integral. You don't need the plus c. It's not indefinite. I don't need the plus c because it actually is involved in both of these and it cancels. We'll see that better later. And we just proved it's equal to this. No plus c in it. Right? So what is the antiderivative of 4x? Yeah, so the antiderivative of 4x is 2x squared. So this would be 2 times 5 squared minus 2 times 2 squared.
Do we just like...
Are you guys with me?
Do we leave out the C?
He just said that it doesn't matter.
I have a whole C spiel I just did.
Oh, no, it's
That's all right.
And the dx, because that canceled out, right?
Say again?
That dx, that canceled out or something, right?
Again, this dx, this is what I meant earlier. It completely has a reason and a meaning. But when you set it up in this format, and we've just proven that this is true, it's not like it doesn't do anything. But the way to look at what it's doing is it's just making sure you understand you are taking the derivative with respect to x. If I was taking the derivative with respect to y, the answer would be 4xy. Because 4x would be a constant. related to y. Is that sort of, and that's not completely 100% true, but it is true for a certain type of integral, so screw it. Right? It's enough. It's true enough right now. All right. So what do I get here? Hopefully 42.
50.
So here you get 50.
minus 8.
Kicking the ass. Now that is preferable, just a little bit preferable to the heinousness on that. So now you're going to be all like, well, what the hell did you want to do that? Or you got to do this like chapter 2. You got to understand where things are coming from. And you could actually, to tell you honestly, I was thinking about doing this and then decided not to. You could do this whole process, but instead of having like from 2 to 5, you could have from 2 to x. And then through this process, you can actually show what the antiderivative, that it is the antiderivative. I decided not to. It was enough to do this, I think.
Yay.
So let me give you guys several to try right now, immediately. Because this is so stupid nice. So I want you to really realize what's important here. You find the antiderivative of this, which is what 4/8 was all about. It's old news. Find the antiderivative of this and evaluate it top first minus bottom, always. So, try these. Oh, what you got, Jeff? Let's use it. Why am I being so evil? And just make that like that. Sorry. I was trying to be nice and that was evil. So in the second one, make it just e to the x inside.
There should be parentheses under number 1.
Yeah, as long as it's the nice thing with the bookmarks is they act like that. They capture the inside. I could put parentheses in there, but I never do because that is contained within this. So these go together to make the integration function. Whatever's in the middle of them is what you integrate. Now, depending on your teacher, some people do this. They do integral dx, and then they put the function here. So they kind of collect all that together. And that's crap. If they do that, they're wrong. It's just different, but I don't like that.
The derivative of e to the x is just e to the x. That would make the antiderivative just e to the x too, right?
You gotta love it. E is just the nicest thing both ways. Let me do something real quick just to help us with how to do this step really nicely. Help me out. What's the antiderivative of this?
X squared minus 9x.
And so what's often done is we'll say between, we'll draw this line, and we'll say that represents this evaluated between -1 and 4. So then on the next step, I could plug a 4 in, minus plug a -1 in. Now notice, there's a minus in the fundamental theorem, and there could be negative numbers. Be careful with your negatives. You got to subtract the whole second part, right? So it's going to need parentheses. The negatives got to distribute. You guys kind of with me? That's the easiest place to make a mistake. I don't care what level math you're in. And real quick, if I did put a plus C here, now you guys can definitely see that it doesn't make any damn sense. So it would be 4 squared minus 5 times 4 plus C minus -1 squared minus 5 times -1 plus C. C's cancel. That's why the C's, we don't even write them. Because we know they're going to go away anyway.
Is that notation necessary though, or like that?
The bar,
Yeah.
it's the easiest way to tell yourself and others what the hell you're doing. Right? So it's not too bad, right? What do you got up here? You get -4 minus 6 plus 5, yeah. -10.
4 squared minus.
Now don't forget, the beautiful thing about these problems is you can put this into y1 in your calculator, go there to the integration function, and say from -1 to 4 and check yourself. Right? Check yourself. Somebody already told me that it's going on here. What's going on there? Yeah, the integral e to the x is e to the x. And I want to evaluate that between natural log of 7, natural log of 11. Good. It's e to the natural log of 11 minus e to the natural log of 7. Is that cool?
It's very cool.
Equals 11 minus 7, 4. I like it because e and the ln cancel. Now here, there's one little thing. Now here's what I was talking about a while back when we first learned the antiderivative. What is the true antiderivative of this?
ln
Absolute value of x. Why does that not actually matter? Because my inputs are all
Positive.
If they were all negative, then I would need it, right? So that's what I meant. You just use it when you need it. You know it's there if you need it. So here I don't need it, so screw it. I just need natural log of x from 1 e to the 5th. Natural log e to the 5th minus natural log of 1. Good. Doesn't that kick so much ass?
So much.
So easy right now. Appreciate it.
got all excited.
Appreciate it right now.
Don't enjoy it too much.
No, that's good. So there was.
This is funny.
Let's see. So if I had what's can anybody tell me? I kind of skipped a very important thing. Trying to get to the don't worry. Look at that. Hanging your head. What's wrong with this question here? Why is that off the bat not going to work? Yeah, because it includes where a point where the function is undefined. So the big part of the fundamental theorem of calculus is it's required that the function you're using is continuous on the interval a to b.
What is the area under the function char if the function is defined at that point?
Do it one more time.
What is like the area under a function char if the function is defined at that point?
If in this case it's undefined because it goes to infinity, right? So the area is going to become infinite. So it's sort of the same thing as saying a limit is not defined, does not exist. But you can be more specific and say it's infinite.
Gotcha. Okay.
Good. So this would be really kind of strange. And in one sense, you could say that this is 0 in a way, but it's actually indeterminate, because what would from -1 to almost 0, wouldn't you get negative infinity?
Yes.
And then up to 4, wouldn't you get positive infinity? But they're not really the same. You can't say that it equals 0. You just can't do it, right? The fundamental theorem says you can't even do this. Don't even try to figure out what it is. Stop it. You're not allowed to use this.
Even
It doesn't work.
function.
See it?
Even an ln function. Will that work as well or not?
Do it again.
An ln function, just ln.
Oh, ln. Yeah, if I had an ln in there. Now, of course, this thankfully is not doable because we don't know what the antiderivative of ln is.
Yeah.
You with me? Not yet, exactly. It's actually one of the first things you learn in Calc 2 is how to handle that. Yes?
Wait, but since the antiderivative is ln of absolute value of x, and then we plug in -1 with absolute value of -1.
See, that's the problem. You think you're okay. You say that ln of x from -1 to 4, and then you get natural log of absolute value of 4 is 4 minus natural log of 1, and you're like, oh, the answer is natural log of 4, everything's great. And what you're not realizing is there's a whole middle part that the fundamental theorem of calculus allows you to ignore as long as your function is continuous. So the fundamental theorem says, whoa, you can't ignore that shit. Your function's not continuous. You can't ignore it. You can't look at the end. You see, so the beautiful thing about what we just did is the integral, the area between these 2 points, just depends on the values of the antiderivative at the ends. That's why your function's got to be continuous in the middle, or else the whole thing goes to shit. Are you guys with me? No. Shit. I was hoping a little bit more for something.
Makes sense.
All right. One example of a type of discontinuity you could actually handle. If you had a function that did this,
It's just like form a little invisible wall for the area or something.
you want to go from 0 to whatever. Now this is discontinuous, right?
Yes.
But how could you handle this anyway?
The sum of individual ones.
Integration by parts is the technical name for a process you learn in Calc 2, but I know what you mean. You don't integrate from 0 to b, you integrate from 0 to
That point.
a, and then from a to c. Because then you can get this area, add it to this area,
From 0 to
add it to this area, right? You guys got it with me?
With you.
So as long as you can break it up and it's continuous on some sub-intervals. So that's kind of an extension of the fundamental theorem. Fundamental theorem is a little too broadly not receptive. If we can break it up like this and it's continuous on each of the sub-intervals, you can still do the integral because you're going to break the integral up like we were talking about earlier, right? You make this integral from 0 to a plus integral from a to c plus integral from c to b, and it's fine on each of those intervals. You with me? A little bit? Sort of? Okay, I'll take that.
Is absolute value usually 0?
Well, it depends on what interval. You mean integrating the absolute value?
That's true.
Yeah. I mean, something like the absolute value, I always kind of hate that function, to tell you honestly, because it's kind of hiding what it really is. It's not a single function, it's 2 functions. And it's trying to, oh, I'm a single function. No, you're not. Screw you. So when you want to try to integrate, that's what it sounds like. If you want to try to integrate absolute value and you're going from, well, if you're going from 1 to 2, you don't need the damn things. You throw them out, it's easy, right? But if you're going from -4 to 7, then you have to split it up, and you can split it up, of course, across at what point? 0, because that's where everything changes. Okay. So they can say this is -4 to 0 plus 0 to 7. Now, for negative numbers, what's the absolute value of x?
Negative x.
I love it. Now, this is the true nature of the absolute value coming out. It's not a single function. It is 2 separate functions, depending on where you are on the number line. And then you just do those 2, and you add them. So, finish this out. What's the antiderivative of negative x?
Negative
Negative x1.
Antiderivative. Antiderivative. What would you take the derivative of to get x?
Wait, no.
Negative x over
x over
2?
2 squared.
So this is weird because this is kind of like manual transmission. I can hear all your brains are like, so what really sucks when you start learning integration is differentiation and integration are complete opposites. So your brain kind of goes first and like, no, I'm not supposed to go. So, yes, it's got to come from x squared.
Negative 1 or 2.
But it's got to be over that new power, right? And of course, it's negative because there's a negative. So I want to evaluate that from negative 4 to 0 plus, and of course, that's the same damn thing, except not negative. From 0 to 7. Yeah, and you just plug the numbers in. You guys semi with me on that?
Yes.
I'm with you.
Most functions are not as deceptive as the absolute value. But something like 1 over x has obvious problems. So you just can't go across that problem, right? You can't go from one side to the other. This problem's not that bad. You just have to split it up. Okay. So look on page 398. And this is the last thing we're going to talk about. It's going to be very quick. Indefinite integrals is actually just section 4.8. Indefinite integrals are just antiderivatives with the whole plus c thing. So when do you not need the plus c? When you have a definite integral. Definite integral meaning it's well defined. It goes from 1 to 7. When you need the plus c, when you don't have those numbers. So if I had integral of secant squared x dx, what that represents is just purely the antiderivative plus c. So what is the integral of secant squared? Tangent. So it'll be tangent x plus c. Cool. So when it's not definite, when it's indefinite, it really is just section 4.8. It's just purely the antiderivative. It hasn't been told what to be evaluated between yet.
So what are forms of indefinite integrals? Just mostly trig functions?
No. It could be any damn thing that we know. So it could be, what else do we know? I can think of that as
Trig functions are indefinite integrals.
So it could be there.
Really, keep like differentiating and then wondering when I'm getting different answers.
That's what I'm.
So trig functions are trig functions. I can take the indefinite integral of any damn function. Integrals are based on antiderivatives, but if I'm not given values to plug in, the answer is just the antiderivative, but this plus c makes it what's called a family, of functions. Because I changed c and I get a new relative, right?
You wouldn't see.
Because it's a family.
Oh, you answered my question, actually.
Good. You're going to ask about relatives?
Yeah.
All right, good. So what's this one here? Good, I love it. The negative ones are really deceptive because you think -5 or something. You got to go backwards. You got to add 1.
5 by what's the which -3?
Coolness. So definite integrals, you don't need the plus c because they would cancel. You should end up with that actual number that represents the area. Indefinite integrals, there's no area specified. It's got to just be the antiderivative. That would be what you would use to figure out the definite integral. Right?
So indefinite integrals are basically just that integral sign with nothing on it.
Beautiful. Indefinite because it hasn't been specified what it's between. Yes, sir.
I got a quick question. So, before you did the derivative of, not derivative, the integration of of sine t dt, and we ended up with just sine x, and on there we end up with 10x.
Careful, careful. Be really careful. What you're talking about from earlier was we had this.
Yeah.
We did not do the derivative, the integral. We took a derivative. So if I do g prime,
Derivative of sin A of x. Yeah.
so this is sine x officially by the, yeah. So real quick, now we can do this now. Of course, some of you guys are going to realize this is cheating a little bit because I'm using stuff that we proved by this, but screw it. If I do have integral from a to x sine t dt, what is it? This is a definite integral. So what do I put there?
Sin x.
No. Don't make me cry.
Oh.
That's the derivative of the integral. They cancel. It's like square rooting and squaring. They cancel.
So is it
Am I taking a derivative?
no.
No, I just want you to do the integral. So what's the integral of sine?
Cosine x.
Negative cosine because it's got
Negative cosine of t from a to x. Now stay with me, stay with me. Isn't that what we were just doing earlier?
right.
And actually we just did it over there sort of, but now we got a definite integral. You guys with me?
Yeah.
So you had a good point. This is not integration. This was if I have, guys, if I have a function based on the integral, its derivative will just cancel that integral. Basically. You with me? That kind of only makes sense because we just proved that the damn integral is the opposite of derivative. So of course they're going to cancel each other out like a square would cancel square root.
Yes.
Here I'm asking you to actually do the integral.
And after this, then that's where I get to do the whole like big F of b minus big
Yeah,
F.
now what's this? Go, keep going.
Negative cosine.
Or
X.
X minus negative cosine of x.
So yeah, I guess.
Plus
Or
cosine.
plus cosine, right?
Oh, it's
Minus negative, right? Minus negative cosine A, you with me?
Plus C.
That was the two negatives, you gotta be careful.
Is it
So this would be like, this is g of x, you with me?
yes.
Yeah. But you forgot the C.
you don't need it when
You need to because it's
Because it's a definite integral.
Oh. Okay.
Good try. So what is g? Now we use the fundamental theorem part 1 here directly. Now I'm trying to get you to use part 2 first and verify part 1. And again, I already said that I'm cheating because who cares?
so you
What is the derivative of negative cosine?
get cosine or
Sine.
Sine.
Sine x. And what's the derivative of cosine A?
A is a constant, right?
A is a constant.
0.
Thank you. Go ahead and I get the same damn thing.
Yes.
Yeah.
Miracle.
So real quick. Here I actually applied the integral, and then I applied a derivative. Of course they should cancel each other out, and I could see it happening a lot more explicitly. Here is saying that same thing, but just going straight there, just taking the integral out of the way. Yes, sir.
I know you just said it a couple seconds ago, but how did you get from taking the derivative of negative cosine of x plus cosine of beta equals sine of x?
What is the derivative of negative cosine x?
Sine of x.
Yeah, and what's the derivative of cosine of a constant? 0. Cool. I like it. And that's the whole thing. And again, this is not, if you really think about it, this is an unsatisfactory reason.